Okay, I'll start with a quick overview of the results which have been obtained for a long period of time. I think now there is sort of consensus of what can and cannot be achieved. Ideal magnetic acceleration. And here's a quick overview of what I'm going to say. So first of all, the process of ideal magnetic acceleration is very slow. Like it takes many decades in distance in order to get a significant acceleration. Then it's closely related to a continuous collimation of the flow. If there's no collimation, there will be no acceleration. Collimation in this case is like a bunching of magnetic field lines. So magnetic flux should get more and more compressed towards the axis of the flow. Otherwise you don't get acceleration. Okay. Then, well, this process by itself requires the flow. Well, it's basically driven by the departure from the magnetostatic equilibrium across the jet. Yes, so this bunching of magnetic field lines. And in order for the flow to know that there is, let's say, departure from a magnetostatic equilibrium, there should be causal connectivity across the flow. So the outer regions, well, if you go perpendicular to the radius, yes, perpendicular to the axis, the outer regions should know that, say, the inner region are out of equilibrium. Right? If they don't know, if it's not possible to communicate between all those regions by means of magnetosonic waves, then there will be no response to any departure of the equilibrium. There will be no bunching magnetic field lines. There will be no acceleration. So the connectivity.
Doesn't these first two lines already give a very strong limits on what sources could actually this magnetic acceleration could be relevant to?
Yeah, I think so. I will come to it later. Just a little bit more. Okay, so for example, in order to have this causal connectivity, we need to have very narrow flows. And it has to be externally confined, narrow flows, and well, how narrow? For example, if you want to have an effective conversion of energy, so half of the original pointing flux is converted into kinetic energy, then the half opening angle of the flow should be less or about 1 over gamma, which you reach at this point.
Why?
Sorry?
Why is that?
I'll come back to this later. This is just an overview, right? Okay, and now if you say that the gamma is about 400, well, this angle becomes very small. And it shows that for GRB it's not suitable. It's to small angle statistics. GRB you will not be able to explain if jets are accelerated in this way. And well, even if you have such a highly collimated flows, the best you can get on the reasonable scales is a conversion of only half of the pointing flux into kinetic energy. So it's like a partition between pointing and kinetic energy, and perhaps this is too weak to explain to get internal reverse shocks, which will give you significant dissipation. And that's probably Dimitri's and Miguel will comment later on this point. Okay, so what's the alternatives? Perhaps the acceleration is magnetic, it can be magnetic, but it's non-ideal, so non-ideal effects perhaps important. Once again, I'm interested to comment on this. And later, well, the acceleration of say GRB flows is effective, but are non-magnetic. Pure pressure-driven acceleration, that's another possibility. And it's possible the acceleration is magnetic, but not effective, in the sense that GRB jets will remain pointing dominated all the way until the point where gamma rays are produced. So this is a beautiful advantage model. There could be some other possibilities which are coming to my mind. So if you have some other ideas, please comment later. Okay, so now well, the real discussion starts. We'll try to explain all of this previous statements, where they come from. So we'll consider this sort of classical subject, or axiomatic steady state, ideal image, the cold flows. Okay. A lot of simplifications, axiometry, steady state, ideal, cold, just to make the problem treatable, and of course, well, this equation comes is well our reasonable also approximations. Well, it's a big question. Well, at least, well, all I can say is that well, this is just for the sake of simplicity. Okay. It could be that there are quite important aspects thrown away because of this approximation. Okay. Well, this is sort of our first step. Right. So let's see if we what kind of results we get immediately from those assumptions. We'll start with the Faraday equation, time-dependent Faraday equation, and the perfect conductivity condition, and use the fact that it's axisymmetric. So we immediately get the result that phi component of the electric field should be 0. Yes, and if phi component is 0, it means that the colloidal component of velocity is parallel to the colloidal component of the magnetic field. This term was vanished, so we get this result. Then, right, okay, what else? Yeah, the colloidal component of our electric field must be perpendicular to the colloidal component of magnetic field. Once again, from this result, straight away. Yes, and also, yeah. So come back to this plot now. So let's say that this is a magnetic field line. That's axisymmetric magnetic flux surface. Right. If you choose the basis where well this vector is just a unit vector along the phi component, this is a unit vector along the magnetic field line, and this one is perpendicular. Both of them that three important vectors have the following components. So colloidal component of B, well, 0, there's no component in this direction, yes, phi component, electric field is only component in this direction, and velocity, colloidal along the magnetic field, and azimuthal component.
Sorry, Sergey. IV is parallel to the magnetic field line, isn't it?
Yes,
so
it's parallel.
B should be parallel to
parallel to the colloidal component.
Parallel to the colloidal component. Okay.
Right. So also you will see from this plot that E, the electric field, is perpendicular to the total vector of magnetic field. Yes, so you can write it as a cross product with some other vector, and this vector has to be azimuthal in order not to get the azimuthal component of the electric field. Okay. Now you can write well this vector as well I phi unit vector in the azimuthal direction, multiplied by some factor written in this form. R is the radial distance from the axis. Yes, and if you substitute now this expression into this equation, you immediately get this result, and it tells you that all this omega which you introduced here must be constant along the magnetic field lines, and you can interpret this as angular velocity of the field line. So the whole field line rotates with a certain angular velocity. Right, and that's what it is. Okay, so in terms of the energy transport along the jet, we are interested only in the colloidal fluxes. We do not bother about the fluxes of energy in the azimuthal direction. And if we write down the expressions for the rest mass energy flux, total net energy flux, and the pointing flux, you will see that they're all parallel to the colloidal component of the magnetic field. Okay. This is how it's shown here. So this is the magnetic flux surface, and all those fluxes are parallel to the colloidal component. Yes.
Just want to make sure that I understand. Omega, the angular velocity, If I'm thinking of a scenario in which the magnetic field is anchored to, say, a neutron star or like, and let's say that omega is non-constant on the neutron star, that means that some of the assumptions here has to fail.
What do you mean non-constant on the star?
Right. I mean, let's say the star rotates but changes its velocity. So spin off. So
Oh, well, in this case, yeah, well, but this is generally a very slow process. Another way. Since I say that well, this is steady state, I assume that everything is constant. Everything is constant. Right. And anyways, there'll also be, well, if there's some time variability, say, variation with characteristic time, it tells you what sort of scale, length scale we should have where you can assume that the quantity is constant. So it will be applicable to a certain range, length scale. Okay, so all these are important energy fluxes, are lower ones that follow magnetic field lines. Right, so the next thing that we can do is to write down the conservation laws for all those for energy and so for the magnetic flux. So once again, what we have here is this axisymmetric magnetic flux tube, and there are well, sort of two nearby magnetic surfaces, yes, and ds is a cross section perpendicular to the surface. Yes, it has well, ds sort of area of this cross section, and because there is no energy flux perpendicular to the magnetic flux surface, yes, well, the flux through this area is conserved in electromagnetic field. Right, so we have well these laws. That's the conservation of proper rest mass, that's the conservation of energy, and that's the conservation of magnetic flux. Okay, so now if we divide well this equation, say by this equation, then we end up with some constant as well, right, along the field line, and well this constant denoted as kappa, so I will use it later, so I write it down here. Okay, then if you divide well, this equation by this equation, you get another constant along the magnetic field line, and it's denoted here as gamma d. Okay, so SE is a total energy flux. No, it's electromagnetic flux. Wait. Okay, gamma is the local Lorentz factor of the flow. Okay, now what is the meaning of this gamma rim? Basically, it's the maximum possible Lorentz factor which you can achieve by magnetic acceleration, and it's clear to understand. So with the pointing flux turns to zero, yes, then all the all the electromagnetic energy is converted into the kinetic energy, yes, so you get the maximum possible Lorentz factor. So this term vanishes and gamma equals to gamma. So yeah, and well, this quantity here is defined as sigma. Well, there is a different definition for the sigma. It's a ratio of the kinetic energy flux to the of pointing flux to the kinetic energy flux. Right here it's a different definition, right? It's a ratio of the pointing flux to the rest mass energy flux. This is how Michael originally defined his sigma, right? And defined it at the inlet, right? At the start of the flow. Okay, so you can measure it. Well, it's in a boundary at the start of the flow at the inlet. And this is exactly what Michael called sigma in his models of image accelerations with pulse. Okay. So if the initial Lorentz factor is small, so this gamma is small initially, then gamma in is basically equals to micro sigma. Okay, and it's micro sigma which tells you what kind of maximum Lorentz factor you can get in this process of ideal acceleration. Okay, do I need to, do I need anything else? This one, gamma in right here. Right. Now, well, it's if you have an expanding flow, then sooner or later the magnetic field line will cross the surface where its linear and linear velocity, rotational velocity, will be equal to the speed of light. Right? And this distance will be called, and this surface where this is satisfied for this particular field lines rotating with this omega will be called now as a light surface. For highly magnetized flows, this is basically the same as the outer surface. So beyond the surface, the flow becomes super alpha. Right. So, okay. So what's written here? So we've seen this equation, yes, for the electric field in terms of colloidal magnetic field and the angular velocity of the magnetic field line, and this is just a perfect conductivity condition. So we see them in terms of the azimuthal and colloidal components of both fields. If you combine the equations together, you'll find how omega and r relate to this colloidal and azimuthal components of those two fields. Okay, so now here is the light cylinder definition. Omega multiplied by the radius of the light cylinder equals to the speed of light. And now let's say that this magnetic field lines crosses this light cylinder. Field line, symmetry axis, light cylinder. So we are moving along the field line beyond the light cylinder. And omega r then becomes much larger than the speed of light. Yes, when you look at this equation. So this quantity is much larger than the speed of light, but this is definitely smaller. Okay, and therefore omega r becomes equal to this third term of the equation. So we end up with this result. Right? And now from this equation you can find the ratio of the azimuthal and colloidal components of magnetic field. So here it is. And colloidal velocity is also less than the speed of light. Yes, but omega r is much larger than the speed of light, so this quantity is much larger than 1. And it tells you that the azimuthal field becomes much larger. The azimuthal component of magnetic field becomes much larger than the colloidal component. Okay, right. So next, what about the electric field? Then we have this equation. Yeah, from this equation we have this expression for the magnitude of the electric field. Yes, now we will use this equation for which relates the colloidal component. Substitute the result of the colloidal component here, end up with this result. And beyond the light cylinder, Vp in fact becomes very close to the speed of light. So Vp is for the C, and it tells you that the electric field becomes a further of the azimuthal magnetic field. Okay, very close. Right, so finally, this is the expression for the Poynting flux. Yes, I substitute this expression for E in here. Yes, and then substitute the expression for B phi. From this equation, you end up with this result. Right, well, it's not clear why, at the moment it's not clear why this result is important, but it will be clear on the next slide. Right, so SE equals 2, C equals 1. R, C,
ask whether the omega r is the real velocity of the fluid.
No. It's just velocity of magnetic field line. Yes, because fluid actually streams along the magnetic field lines itself. It have different. It definitely has a different as a uniform velocity. Right?
Just a number.
Yes. Otherwise, it would be superluminal. Can have superluminal.
So you just defined omega r and actually something
Yeah.
physical.
This is not.
same, or-
Yeah. This omega is not the angular velocity of the flow. It's
Mhm.
not the rotational angular velocity of the flow. No, it's only the rotational velocity of the magnetic field line.
But field line still is rotating with that omega.
No, okay, so you imagine now this helix, yes? Now this helix is rotating, yes? But the flow rotating, I don't know which way. It is this way. Yes, but your fluid element is actually moving along the field line. Yes, and therefore its angular velocity will be different from the angular velocity of the field line itself. Okay?
That's acceleration.
Right?
I'm confused. This is only the force free. MHD omega is combination of both. The field line and the.
Omega 1?
I mean, in MHD, it's only force free case. In MHD, the particles should only move along polar surfaces. They can have. I mean, this omega is a combination of the
It moves.
field
Well,
line
this,
and the
this is your colloidal surface, yes? So this is your colloidal field. And this is your azimuthal component, magnetic field, right? Yes, so the particle, yes, it moves along the magnetic surface.
Yeah,
Yes,
but
but it
omega-
also participates in some rotation.
Right. So omega is a combination of both, the field rotation and the rotation of the.
Omega is, well, this omega here is only the angular velocity of the field line. And if you come back to the previous slide, so here how it relates to the angular velocity of the flow. Okay, so this is the linear velocity of the field line, rotational velocity, yes? This is the linear velocity of the flow. They are not the same. They are not the same because there is non-zero VP, yes? Non-zero colloidal component of velocity. Yeah, so this is where I'm going to use this result. Okay. So basically I have this equation for this constant along the magnetic field lines, gamma link, and here is this expression, this pointing flux. So basically what I will do, I'll substitute this expression into this equation. Yes, and now we will write the result in this form. It's gamma plus some constant along the magnetic field lines, gamma n, multiplied by some variable function, which I call the Bachin function. Well, this constant is, well, the combination of the angular velocity, total flux enclosed by the magnetic surface, this magnetic flux surface, magnetic flux going through this area. Yes, and copper is this constant along the magnetic field. Okay, so this is all constant, this is only quantity which varies. And this is the expression for this quantity. And for this function, which I call the Bachin function. And so this is R, distance from the axis, strength of the colloidal magnetic field along this field line. Yes, and this is a magnetic flux enclosed by this magnetic surface, which determined by the rotation of the field. Okay, and the variation basically of this function along the flow which governs the acceleration. Okay, if this function varies, then gamma varies. If this function is constant, then gamma is constant. Okay, so now let's see what kind of result you can get for this FB if we have, well, the distribution of the colloidal magnetic field across the jet according to this law, or this power law.
Where did the first equation come from?
Which one? This one?
Come back.
It's here.
Okay.
Yeah? So, conservation of the total energy, conservation of the response energy divided, and we get, well, this is.
Okay, sorry.
No, it's fine. Right. Okay. So yeah. So basically, take well this dependence for the sake of the exercise. Yes. Take this dependence for colloidal field strength. Substitute into this equation. All right. To find the B. Well, you see that the B is a function of lambda, a function of this power. Right. And yes. So now take a look here again. So in order to increase gamma, what we need to decrease, well, this function of B. So smaller if B becomes, larger gamma becomes. And if a B say decreases by a factor of 2, then basically this term will become equal to this term. Okay? Well, let's start again. So initially, well, this term is dominating. The initial noise factor of the flow is very small, right? So this is also sigma, which is very large, right? So if B decreases by a factor of 2, it means that, well, this term becomes the same as this term. Okay, so gamma becomes as large as half of the maximum possible. Okay? And so at this point, we will reach a equipartition, basically, where the kinetic energy or the matter energy flux will be equal to the point flux.
Just colloidal field disparity doesn't say convert it to flow.
Right.
This combination gamma plus gamma if B thing is a constant, you say. And
Yeah, this is constant, yes.
and we assume
And this function depends on the distribution of the colloidal flux within this magnetic
so
flux.
acceleration is due to something conversion from dp to some flow kinetic energy. You just say. Yeah, just you say that.
What I'm saying, what I'm saying is that, well, acceleration actually depends on the redistribution of magnetic flux within the flow.
This particular form is a solution of the Grashev-Ranoff, or where did you get it?
This one? No, it's not a solution of
Just,
Grashev-Ranoff equation.
for
It's just for the sake of the exercise, for the sake of demonstration. Yeah? So, let's say that our colloidal flux is distributed uniformly,
Okay.
yes, initially, across the flow. Yes, so lambda is 0, and this function of B is unity. Okay. Now let's say that lambda is -1, so magnetic flux is compressed towards the axis. Yes, and FB becomes half. Okay. So this is one distribution of magnetic flux, uniform magnetic field. Yes, uniform distribution, and this is a distribution where magnetic field lines are bunched towards the axis, compressed towards the axis. And this is and you see all FB indeed, well, in this case, will decrease by a factor of 2. Yeah, and you get due to this redistribution, you get a sort of very, well, more or less effective acceleration. So the gamma becomes half of the maximum possible which you can achieve.
You mean
Right.
when you go from the equal distribution to this
Yes,
bunch?
to this one, yeah. Basically, the point here is that you need to organize all this bunching of magnetic field lines towards the axis in order to get acceleration.
In this case, lambda equals to -1, don't you have a divergence at the axis? Doesn't it give you a logarithm divergence at the axis?
Yeah, it will be, the field will be divergent.
Okay.
Also, you can
But magnetic flux will
It's
not
fine.
be divergent.
If you integrate from 0?
No, it's not, because, well,
It's not
The
finite.
squares, not the
you have
right, because it's divergent, yeah.
Core.
So it's divergence here cancels divergence there, so it becomes, it's just a finite number.
So,
Okay, so you have this divergence, but it's just to show the idea.
Oh,
right?
okay.
so, in terms
Obviously, it cannot be like that. Also,
No.
it's axis.
so physically what happens here is that you're converting the energy from the colloidal part of the magnetic field to the rotation of the magnetic field, right? Because B phi is much larger than BP.
No, I wouldn't say that. It's not the energy of the colloidal field.
Just something compressed, that give you energy, or something need to bounce field.
To compress the field, yeah.
This is
Yeah,
energy source.
yeah. So, well, I wouldn't say this is energy source. Energy source is pointing flux.
Or it's not the energy source. Okay.
You have a pointing flux. And this is the source of energy. You want to convert all this flux into the kinetic energy flux. Right. So, in terms of the fields, it's a combination of basic azimuthal magnetic field and radial electric field. You have those two fields, well, energy is stored in those fields.
So this bounce is expected naturally to happen.
Yeah, this bunching helps the conversion. Well, this is all I can say. Well, I don't have any simple explanation or like a layman or basic physics explanation what actually force does work.
But your wall in the end plays a role. I mean, in the end, the external medium or the wall, let's say, plays a role for how this process.
Yes, it can.
proceeds. So
Yeah,
it's-
yeah. It can help the bunching. Yeah.
So,
But basically, or well, we will come back to this. Yes.
Okay,
But effectively, you can think of this like that. So you have a rotation, right? Initially colloidal field, well, close to the axis, close to the source. It's mainly colloidal field. And because of the rotation, also some light cylinder, and because of the rotation, azimuthal field is generated as well. And it's stronger at the in the region which is closer to the outer edge. Yes, because it's being the light cylinder. Okay, so now we have well, this azimuthal field, and what it does is because of hoop stress, yes, it's pinching the flow. So this pinching can give you well the required bunching of the colloidal magnetic field lines towards the axis. Okay, so this is how the process of bunching can occur naturally in the flows. Yes.
What if you turned off the rotation and you just kept this shape of the field lines? Wouldn't you get the nozzle effect anyways? Why is rotation important? I mean, for
Well,
if it's a dipole, if you put -3 there, it will be diverging field lines, and you will get deceleration.
deceleration of the initial flow.
Well, if I just plug in
It's just cold flow.
if I just
You
plug
won't
in
get any.
-3
You won't
there,
get any deceleration.
yeah.
Particles will just on the field line. There will be no acceleration or deceleration.
There is no azimuthal component.
Well, why does a jet engine work?
I think you need it for the drug, right? Jet engine.
Yeah, jet engine doesn't rotate. All it
Oh,
does.
it's gas dynamics. Yes.
Yes.
So you have a lot of thermal energy, and the thermal energy which gets converted into the kinetic energy.
But all you're doing is changing the shape of the.
Oh, right. It's a nozzle effect. Yeah, that's what you're saying. So is the flow.
Yeah.
Let me put it this way. So this is a nozzle, yes. So if so basically if the flow is supersonic, yes. This is the nozzle. This is the chamber. Okay. So here is the flow is subsonic. Here the flow becomes supersonic. Yeah? Okay. And as far as the subsonic, it's a this sort of conversion from the walls, yeah, towards the axis, which gives you acceleration in the subsonic regime. But in the supersonic regime, it's a divergence, yeah, of the field lines which give you acceleration.
Right, and that's
So-
all subsonic.
Yeah, that's different. Well, here's a different story.
Because we have 3 critical points. In the hydrodynamic case, there is only 1 critical point, right? So it's, at the critical point, the Mach number must be 1 for this wind solution, or you have shocks. That's another possibility. I mean, in general, you have shocks initially. It's only-
Yeah, well, there are some shocks, so
Well,
this surface must be tuned,
There is only one
right,
solution.
very well tuned in order to avoid shock formation. Well, straighten the nozzle and all that. Well, they will form later. Anyway, m equals 1 is around here. But that's a completely different process. Yeah. There is a difference in MHD.
So that is the slow. I mean, in force free there is no slow point. That would be the slow point.
Here is a slow point.
And,
Yes.
But I have another question. I don't understand.
So here we assume that the flow is already pushed with some small Lorentz factor, some small velocity. So it keeps flowing and then it gets accelerated when it.
I don't understand this bunching. I mean, the current. What is the current closure path? I mean, it's closed at infinity. If it doesn't close at infinity, you must have after an expansion.
Well, what happens in infinity, that's a different story.
So how can you get?
Well, there is some head propagating there, and the current, because it becomes time dependent now, so the current can be closed just because of the displacement current.
In this picture, if your current closes at the finite, you agree that there must be an expansion because there is a repulsion force acting.
I guess
It must expand it after the speed.
here is just a current along the jet, and it flows somewhere further away, I guess. So
Only at infinity. Or you have external pressure to
Well, for
support.
such-
Yeah, you always have external pressure. You always
Okay,
must
It's
have.
a basic ingredient, I guess.
Without external pressure, it's open and
there
you
are
stop
solutions,
the acceleration.
There are solutions where you don't have external pressure, and then it closes at infinity, and then you have like the solution is a Bessel function, so it has a finite, essentially it culminates, but it's not realistic. So you have an external pressure. Then it should depend on the pressure or what.
Oh yeah, yes. Well, you can extend the confining medium, but if you don't have, I'll come back to this. If there is no external confining medium, well, you can still have bunching, but it becomes ineffective at some point. As far as the current closure is concerned, I don't really understand the point. So there will be current flowing this way.
And then close
Yes.
it.
Then it will be flowing back this way.
Now you see
So
that
the total current
there is
will
a
be zero.
repulsion. There is a repulsion force. There are two current. There is a closed current loop. It must expand.
Oh, well, yes. Okay, so we can have some external medium here.
Yeah.
Instead of this gas pressure, the magnetic pressure, which keeps this confined. Yes. Yes. Or the flow occupies the whole space.
So it's really a present.
And then what you will have, it's this is your central source, yes, and you will have something like current flowing in this direction, and say split monopole coming back into the oil point.
Infinity.
Yes, and it closes at infinity. And as I say, in reality, if you have some propagating wave, right? So the current closure, if it sort of expands in vacuum, for example, right? In vacuum, that this can be just a displacement current which provides you the current closure.
But for this, the question is for this situation you can get this solution.
And as far as the confinement, well, there is no confinement. Well, there is magnetic pressure here, is bound by the magnetic pressure there. So, and it's already expanded, it's already occupies the whole space. There is no issue here.
And no effective acceleration with the
Okay, so now
in a monopoly like this, you don't have acceleration.
some numerical results. Amir.
Yes, sorry.
So,
If you put
so what we have here is a wall, right, which gives you the confinement. It doesn't allow the flow to expand. Yes? Well, in reality, it can be some medium. With some external pressure, we actually can find out what the external pressure should be in order to provide such geometry.
Yeah.
Okay? Right.
It's a point.
So
What
what
defines
shows?
the shape of this wall?
Yeah, so that's a parabolic shape. It's a parabolic shape.
What kind of external pressure?
So what's shown on the plot is colloidal magnetic field lines, yes, and density in logarithmic scale. So if you look at this plot, you already see that there is a compression towards the axis. Okay. Well, initially the colloidal field is distributed uniformly across the inlet, yeah? And then the velocity is constant for this particular example. Okay. So we already see that magnetic field lines are bunched towards the axis, yes? And also density shows you the same thing. There is a compression towards the axis. Initially density was distributed uniformly across the inlet. And this is actually the distribution of the colloidal field across the jet and how it changes with distance. So initially it's constant, yeah? But if you go along the jet, it becomes more and more bunched towards the axis. Okay, just because of those Hooke stress of the azimuthal component. Okay, and well, this plot shows how the Lorentz factor and well the sigma of this ratio vary along the jet. So that's logarithm of distance in units of the light cylinder radius. Okay, so and we have two pairs of curves, well, which correspond to different magnetic surfaces. Okay, so this one is the most distant, most closest to the external boundary. Well, is close to external boundary, and this one is close to the axis. So basically, we'll see that well, the gamma increases, and at this point it becomes half of the maximum possible. So when when this term equals to this term, and this is this point, this gamma is half gamma. Yeah.
So the solid line is in the boundary, or
Yeah, solid line corresponds to the flow close to the boundary.
so it's faster there.
Yes, and this line, well, dash dot line, and this one also dash dot line. Well, that corresponds to some magnetic flux close to the axis.
So it's faster at the boundary.
Yeah, at the boundary the flow is faster. Well, this is a feature for magnetic acceleration. The case where the object to which magnetic field lines are anchored rotate with a uniform angular velocity.
So beat on the wire, something like that.
Beat on the wire. Or bear on the wire. Bear.
Oh, that's usually well. When people say that, they refer to the centrifugal acceleration.
Yes, the magnetic field is also possible.
Yeah, it's a magnetic acceleration, but I'm not sure why.
It's not, because there is inertia here. It's force free, or there is inertia.
There is inertia, of course. Yeah, that's a full relativistic MHD, but we start with the flow which is highly magnetized. So Michael's sigma, you can see, well, it's near the boundary. It's around 600.
Why magnetization is higher at the boundary in the beginning, at the start of the flow?
Well, it's you can understand it this way. So this is a ratio of the pointing flux and the rest matter energy flux. Yes. So and the pointing flux vanishes at the axis. With no azimuthal magnetic field is generated, the electric field vanishes as well. So pointing flux is exactly zero at the axis. Yes. So it should vanish on the axis, and this is how we can understand why sigma decreases towards the center. Okay?
Where is the energy basically? You said that at the boundary gamma is higher. I'm just wondering if actually that portion carries significant energy. I'm just wondering the context of GLD jet or something like this, and example to cause gamma ray burst, we need to have a red disk jet which carrying significant energy. And I just wonder if you cut some point, how it's
how the energy is
energy
distributed. Yeah, well, it peaks near the boundary.
Near the boundary.
Near the boundary. Well, I'll show you exact distributions if you like. I mean, there are such plots in the paper.
How it's possible
I
that,
don't have it here.
but you have very dense medium in the center with the reasonable Lorentz factor. Why it should
Yeah,
be-
but still, most of the energy is still near the axis, near the outer boundary.
But there are two orders of magnitude in density difference.
Yeah. Well, it's not enough. It's not enough. Okay, anyway, this is just a demonstration that how the mechanism works. Yes, how this bunching or collimation of magnetic field lines provide you with some more or less efficient acceleration. I also want to point out here that once this point is reached, when you reach the equipartition of the point flux because to the same order as the kinetic energy flux, the acceleration slows down dramatically. So beyond this point, you can't get much.
Where is the fast point?
Well, the fast point is in fact noticeably closer to the center, so it's something about here, as far as I remember in the simulation. So maybe even less. So here. So the slowing down of this equipartition point is reached well after the first magnetospheric point is passed.
Most of the acceleration happens beyond the first.
After the first point. I'll come back to this.
The fast point is scaled with sigma. For sigma 10 to infinity, the fast point should be at infinity.
Well, sigma is not exactly infinity.
Yeah, but I mean, why is it?
Yeah, but if you push it to infinity, well, obviously you will never, if sigma is infinity, you will never reach this point, and the first point will also go to infinity. But if you have final inertia, then it will always happen in some finite distance.
Yeah, but why you say close? What do you mean by close? You say it's inside.
I mean, it's closer to the center compared to the point where equipartition is reached. I interpret your question in this way, right? You wanted to know where. Yes.
I mean, the fast point is the standard relation between gamma equal to sigma to 1/3 or something. This is the
Yeah, I'll come back to this. Yes, it's related to this. Okay.
This is similar, by the way. This solution is.
No, it's not self-similar.
No, but it's close to.
No, it's not close.
So we can forget about something.
Well, well, there is still some use for self-similar solution. It allows you to see what happens in the particular kinds of solutions, right? So you get some experience from self-similar solutions, but real flows do not have to follow this particular kind of analytical solutions. No? They're different. Okay. Do you mind if I get some water? I'll be back in a second. Well, okay. So as I said, basically, in order to get acceleration, you need to have bunching of the magnetic field lines. Bunching magnetic field lines is basically a response to the loss of the hydrostatic equilibrium. So system wants to restore the hydrostatic equilibrium across the jet, and because of the appearance of this hoop stress. Yes. Okay. But if there is no communication between different areas across the jet, then there will be no. Well, this equilibrium will not be restored, right? And the bunching will not proceed. Okay. If there is a compression near the axis, and magnetic field lines close to the boundary, if there is no causal connection, do not know about this. So they do not move towards the center, because there will be no bunching of those field lines, there will be no acceleration. So causal conductivity is extremely important. Okay? So flows should be causally connected in the transverse direction in order for this process to work. Okay? And
so this bunching thing is okay. So at the beginning, at least we need some boundary, something need to collimate. After some degree it's collimated, only hoops.
Yes,
it's
so yes, the boundary affects the outmost magnetic field line. Yes, but the rest of the jet may not know about this effect. Okay, so magnetosonic waves must be able to propagate inside and transport this information. So the rest of the flow can adjust to these changes at the boundaries. Okay, if magnetic field lines, if magnetosonic waves cannot go inside, okay, if we cannot reach the inner region, then the inner region will not react to the changes in the boundary. Okay, so you should have two buff conditions.
So again, in the simulation you just showed, what is assumed about the external pressure? What is the profile of the external pressure?
For that particular case, I don't remember, but I can
mean,
find out.
the
It's
solution-
certain power law.
The solution depends on this profile? Or?
Yeah, for different power laws, we'll get different shapes of the boundary.
And usually it's near R minus 2 P profile. And for conical way, it's a little bit faster.
Well, I wouldn't say usually because we have different parabolic shapes. Basically, we play with different parabolic shapes. Radius of the boundary is proportional to the distance along with access to some power. Right, and this power will play with different ways, like 1 over 2, 1, 2, and
3.
1.5. 3, yeah, 3.
3 and 1.5. 3 and
Okay, and they all correspond to different power laws of the external pressure. Okay, but this is a minor thing. This is a minor thing. Compared to what I want to say. Okay, so causal conductivity. You begin to lose causal conductivity when the flow becomes supermagnetosonic. And so this is our picture which illustrates the light the Mach cone or the cone of influence. Yes, so this is sort of also the front of the magnetosonic wave originated in the center and propagates with the flow, and this angle determines user area which will be affected by this magnetosonic wave. And the Mach angle is one of the sign of this half-opening angle of this cone. And in the relativistic case, for the magnetosonic wave, it will be given by this equation: Lorentz factor of the flow, trivial velocity of the flow, Lorentz factor of the fast magnetosonic speed, and the fast magnetosonic speed. So that's a ratio for velocities, magnitude for velocities. Right. So let's just start with the unconfined flows. For the unconfined flows, the connectivity is lost as soon, or you begin to lose the connectivity as soon as the flow becomes supermagnetosonic. So in this case, theta m becomes less than pi by 2. Okay. So now, what we can do now? Well, that's the expression for the fast magnetosonic speed in terms of the magnetic field, the uniform magnetic field of the fluid frame. Yes, and the proper resonance density of the flow. So what do we do next? Yes, Vp is basically the speed of light. Yes, so if Mach number is 1, then gamma multiplied by the speed of light squared should be equal to this quantity squared. So we end up with this result. And well, this is, as I say, that's the magnetic field as measured in the fluid frame. If you relate it to the magnetic field as measured in the lab frame or in the source frame, then you end up with this result. Okay. And yeah, let me see what's written here. So here is matter energy flux density. And here, in the brackets, is the Poynting flux. Okay, so we end up with this result. So the matter energy flux at this point equals to 1 over gamma squared multiplied by the Poynting flux. Okay. And well, this gamma is the gamma at the first point. Now, the first conclusion which we make from here is that gamma must be, at this point, must be much larger than 1. And it's clearly can be seen by contradiction. Now let's say that gamma is order 1. Yes? Then what do we have? Then the kinetic energy or matter energy flux is the same as the Poynting flux. So basically most of the Poynting flux is already converted, yes, into kinetic energy. And the Lorentz factor must be high because it's high initial monetization. Okay, and this gives you a high Lorentz factor. So we get the contradiction. Okay, so the Lorentz factor at this point cannot be of order 1, it can be much larger than 1, and therefore the kinetic energy flux is much less than the Poynting. So at the first magnetospheric point you converted only very little of Poynting flux into the kinetic energy. Okay, but the connectivity is already lost. Okay, and your acceleration becomes inefficient. So, in fact, well, we can do a little bit more now, since we know that gamma is much larger than 1 in this point. So, here's again well, this expression. Okay, so gamma is much larger than 1, but it's still much less than gamma lim, so this term is still dominating, so we can ignore this term compared to this term. So we come here, and then we relate the resonance energy flux to the matter energy flux. We just relate it by gamma, additional factor. So we end up with this result. And then we substitute the previous one for the ratio of SE and SM of this result. Substitute it in here, right? Yeah, well, actually it's here already. Substitute it in here, and you can relate now gamma with gamma lim, and you end up with this well-known result that basically gamma is only 1/3 of the Michaels. Basically, Michaels are sigma or the maximum possible to the power of 1/3. So if your maximum possible is 1,000, well, then what you get, the first point is only gamma of order 10. And acceleration becomes inefficient after this point because of conductivity across the flow is lost. Right. Now, the things are a little bit different if you're dealing with the flows confined within a sort of narrow region. Okay, so let's say you're confined within a half opening angle theta. And then, because the conductivity is lost, then the Mach angle is less than this theta. Okay, so we have a different condition for the loss of the conductivity because your flows are narrow. Okay, so the condition is not that severe as for other confined flows. So we do the same calculations as before, and we end up with this result, which relates maximum, basically maximum possible gamma, which you can reach in the magnetic acceleration. Well, the gamma. Well, this is the maximum possible, which can be reached, yes, theoretically, in principle, right? And this is which maximum possible, which you can reach in reality, yes, which you reach in reality as a result of this mechanism. So you have well this theta to the power of -2/3. Okay, right. So if theta is small, theta gets smaller, gamma gets larger. So in principle, for confined flows, you can accelerate to a larger Lorentz factor. Okay, now let's say that we have a full conversion. Indeed, that well, this gamma is indeed the maximum theoretical possible. So we substitute it in here, and we end up with the constraint on the opening angle. So the opening angle of the flow must be of order 1/gamma, 1/gamma lim. So if gamma, yes, yeah, okay.
So Tsarkovskoy seemed to be a bit more optimistic in this sense. They found that theta times gamma can be several or something. I think was it for real simulations that they did? So do you think it's within this factor of a few, or it's something else there that makes this difference of several. It allows for a bit larger opening angle for the same bulk Lorentz factor. That's it.
Well, I think what they say is that there will be still some acceleration after all this connectivity is partially lost. Well, there is still some connectivity across the flow.
That's very slow one?
Yes, it becomes a slow acceleration.
So
They take the slow acceleration into account. Well, that's how it was explained to me.
Okay.
I couldn't see the real calculations, couldn't get through the real calculations, probably from this number. But this is how it was explained to me. So they can get some additional factors.
Sergei, can it be that the flow is getting splitted sort of in the core and the wings, and in the core you still preserve this connectivity?
Yeah, that's another point. So another point to make. So suppose we have a flow. Let's say a confined flow. And this is the axis. Yes, and think about this condition. Okay, so you can take a look at the whole flow. And this is a theta, and then you can consider the inner region of this flow, which has small angle, theta 1, and it tells you that basically for the even when the acceleration is already stopped, most of the flow, yes, it can proceed for the inner region. The inner region can still be connected itself.
But roughly the energy is proportional to the surface? The energy
Yes.
involved in
The energy involved will be small. Will be small. So you can get some extra acceleration if you get closer and closer to the axis, whatever, it will be peanuts. It will be peanuts. Okay. Right. Yes, and this is a demonstration of this. Yeah. Okay. So what we had before we had a parabolic surface, yeah, parabolic wall. So it would make my jet narrower with distance. Yes, so the half opening angle would be decreasing all the time. But here it's conical, and as soon as this condition is satisfied, the condition with the angle. As soon as this you reach this gamma, given by this, you reach gamma defined by this equation, acceleration stops, and you don't get equipartition. And this is the curves again. So that's sigma for the magnetic surface, which is close to the wall. Yes, and this is gamma of the acceleration. You still have the acceleration, but it becomes ineffective. You don't get the equipartition. Okay, basically because the connectivity is lost across the flow quite soon. Okay, that's another case. So you can argue that you can get the bunching just by effective bunching of magnetic field lines just by introducing the diverging walls. Okay, so if let's say that this is a diverging wall. Yes. So initially magnetic field lines are more or less uniform. Yes, but because the wall diverged, the magnetic field lines also want to diverge. And you sort of get like bunched magnetic field lines as a result. Yes? Yes? So you can think about you can still get bunching, you can still get acceleration, but the difference is it now becomes more and more difficult to satisfy the causal connectivity across the flow. So it's lost faster, earlier. And what happens is that the flow begins to ignore this wall completely and becomes ballistic at some point. It becomes a radial flow. and the acceleration stops.
So it's like a rarefaction. Like a rarefaction, right?
Yes, well, this is the front of the rarefaction, basically. This is the front of the rarefaction.
Imagine end of star. When you come through a star, photosphere, nothing.
And as I mentioned, this property of this constraint on the opening angle makes the ideal MHD acceleration mechanism not particularly suitable for gamma ray bursts. So if you want to achieve gamma 100, then the theta, the self-opening angle, should be very small, 10th of a degree. Okay, and then you can sort of estimate, you can compare it with the observed statistics of gamma ray bursts. So what is shown here.
If you say that the acceleration is slow, how long do we need to accelerate? I'm gonna say. Stellar envelope will just.
Once the conductivity is lost. Forever.
So
Yeah,
how
but
long
it
is
effectively
needed?
stops. It effectively stops. You cannot get any much beyond this unreasonable statistical scale.
Yeah, I just wanted the number. It's reality parameter.
So the number is prohibitively high.
Pardon?
It's prohibitively high. Prohibitively high.
Okay.
So you can forget about any acceleration. If you want. Right. Okay. So yeah. So as I say, well, basically the jets will become very narrow. Yes. And we have to be very, very lucky to see such narrow jets. Right. And since we see a lot of them, right, then small angle will increase the real number of GRB explosions. Yes. The unseen ones. Now we compare them with the rate of supernovas, co-collapse supernovae, and what you'll find as a result that right. Okay, so that's the observed rate. Yes, after correction for the beaming of this angle, that's what you get: 3 times 10 to the minus 2 in a year per galaxy. All right, and then the observed rate of 1 BC.
So something
supernova
must be wrong.
is
You say the jump rate is
30 times
higher
lower.
than the rate of the supernova. I think something must be wrong here.
Sorry?
The jump rate is higher than the 1 BC supernova. How could that be?
Required.
That's the thing, he's trying to find a contradiction. But if you take 100 Lorentz factor, it will be okay, because
If you take 40,
yeah, maybe less.
So it proves that the Lorentz factor is 100.
Nobody
Gamma
knows
burst.
Lorentz factor. It's all.
Okay. They have mathematical proof.
So now it's up to you. For small Lorentz factors, yes, you can get something. Yeah.
I don't think anybody will
Out of
complain
this,
too
but
much.
it's if most GRBs have very high Lorentz factors. All of
I know, but this is just assuming that all supernovae will yield
Yes.
this kind of gamma ray burst. If in actuality you take about 1% of them, then maybe the limit on the Lorentz factor is too small, actually. Maybe prohibitive.
Not all is MHD, gamma ray burst.
Yes, but you know, in order to have fast rotation and so on, you have to meet very special conditions in the progenitor. So, according to stellar evolution models, including all possible elements, magnetic field, rotation, and so on and so forth, this is only in a very few % of the cases, right? So, you would expect at least a factor of 100 smaller rate for supernovae that produce gamma ray burst. And then it translates into, I don't know, I haven't made the math, but maybe you get Lorentz factors of 50 or so, less.
On the sun.
Yeah, maybe. So it doesn't look promising.
Did you multiply by 2?
Sorry?
Did you multiply by 2? No, 2 digits.
Yes. Don't worry. I haven't lost it fact. No. Yes. Okay, so basically, probably we need to consider some alternative model. Well, for as I say, well, probably for AGNs it's fine. AGNs don't have such high Lorentz factors. Smaller is fine, but GRBs is more is problematic. And we probably need to consider some alternative models. Let's say perhaps non-ideal effects should be included, or we should stick with purely ballistic, contaminated flows, or maybe it's just as originally proposed, pure gas dynamic acceleration. Yes.
Okay.
That's it. Yes.